In this video, we are going to discuss the fourth example of determination of inverse Laplace transform of a given function. If you have not subscribed to this YouTube channel, I would appreciate if you subscribe to the channel and continued watching the videos online. Now let us go through our example. Our particular example here is October-November 2017 and it's a diploma in electrical engineering module 2 past paper. And we are told we determine the inverse Laplace transform of this function here. So we have our function is fs is equal to s plus 2 over this. The first thing we said we should do is to check whether the function is proper, and we can see the function is proper because here the degree is 3 and here the degree is 1. The next step is to factor out the denominator. The denominator appears to be already factored out for us, but it's also important to check whether this one can be factored out further. So if you check here the product is 5 times 1 and the sum is 2. For us to be able to factor out this factor, we need two numbers that we can multiply to give us 5, and when we add them, they should give us 2. Of course, we do not have two whole numbers whose product is 5 and whose sum is positive 2. And therefore, the second factor here is an irreducible quadratic factor. The first factor is a linear factor. Now we can go to the third step, which is determination of the type of factor. We can now say the denominator is composed of a linear factor and an irreducible quadratic factor. You can say partial fraction will take the form of course in an exam you do not need to write all this. I'm only writing it for purpose of your understanding. So the partial fraction will take the form. We have our rational polynomial function, which is 6s plus 2 over s minus 1 s squared plus 2s plus 5. The partial fraction will be of the form the first factor here, which is linear, a constant a over the linear factor, plus the second factor here, which you have seen is an irreducible quadratic factor. So you have a constant b times s plus c over the second factor, which is s squared plus 2s plus 5. We now need to determine the value of a, b, and c. To do that, we will multiply both sides with the denominator. Multiplying both sides with the denominator, so you have here this side, when you multiply with the denominator, of course the denominator will cancel out, so you only have 6s plus 2 is equal to a over s minus 1 plus bs plus c over s squared plus 2s plus 5. We have said we multiply both sides with the denominator. Here it will multiply and cancel out, but here it will be s minus 1 s squared plus 2s plus 5. Now open the bracket. This term times this term should be 6s minus 2, 6s plus 2. Six s plus 2. When you multiply this term with the whole of this term, s minus 1 will cancel out. So you have a s squared plus 2s plus 5. When you are multiplying this term with the whole of this, s squared plus 2s plus 5 will cancel out. So now that we have only s minus 1. So you have plus bs plus c, then multiplied with s minus 1. We can now open the brackets, which will give us 6s plus 2 is equal to as squared plus 2as plus 5a. We now multiply this and this, which will give us bs squared minus bs minus plus cs minus c. Let us now put the term with s squared, the term with s, and the constant terms separately. So you have 6s plus 2 is equal to s squared. You have a plus b. We have s. We have 2a minus b plus c plus the constant terms, which are 5a minus c. In the previous two examples, I showed you a different method of getting the constant terms without having to open these brackets, where we said, for example, you substitute the terms s minus 1 is equal to 0 and s is equal to 1. It is important for you to run both methods because any of the two methods will come in handy. You can check my previous videos how I made these substitutions in order to get the values of a, b, and c. Another thing that I should mention, a lot of times this term 2s, a lot of the time is usually 0. For example, you could have, instead of having s squared plus 2s plus 5, you could have something like s squared plus 4, where the middle term is 0. This one is still an irreducible quadratic factor. Or you can also have s squared plus 1. It's also an irreducible quadratic factor. But if you have this term here is s squared, say, minus 1, or s squared minus 9, for example, you should be very careful. This one can be factored out further, because this one will be s plus 1 times s minus 1. This one will be s plus 3 times s minus 3. Be very careful with this quadratic term. Always try to check whether it is possible to factor it further. Equating the coefficient of coefficients of s squared, s at the constant on both sides of the equation. On both sides of the equation. Where you have s squared, we equate with the term with s squared. Where you have s here, we equate with the term that have s, and where you have the constants, we equate with the constants. You can see on this side we do not have s squared, or in short we have 0s squared. Therefore it means you have 0 s squared plus a plus b. I mean s squared times a plus b. This is simply a plus b is equal to 0. We also have 6s is equal to s 2a, s into bracket 2a minus b plus c. We can cancel out s, that we have 6 is equal to 2a minus b plus c. We also have the constant 2 should be equated with 5a minus c. You have 2 is equal to 5a minus c. Let us call this one equation 1, this one equation 2, and this one, let us call it equation 3. We can now try to work out the value of a, b, and c. Using equation 1, we have a plus b is equal to 0. Therefore, you can say b is equal to -1, not negative a. We want to get the value of b here or here, so that we can substitute it. We want to get the value of b so that we can substitute it here. So now let us write substituting value of b in what? Equation 2. In equation 2. This will give us 6a is equal to 2a minus, but b is minus a, minus a plus c, or simply 6 is equal to minus is positive, so it is 2a plus 2a plus a, 3a plus c. So now you have two equations. You can call this equation now 4, and then we say using equation 3 and 4, using equation 3 and 4, this will give us, we have 6 is equal to 3a plus c, and we have 2 plus 5a, 2 is equal to 5a minus c. We can eliminate 6 plus 2 is equal to 8, 3a plus 5a is equal to 8a, positive c plus minus c is 0. This means a is equal to 1, and because you have b is equal to minus a, we can also say b is equal to -1. Now we can go ahead and get the value of c. Can you see the equation 3 or equation 4? Let us use equation 3. We have 2a, not 2a but 2 is equal to 5, which is 5a is 1, which is simply 5, and c we do not know yet. We are trying to get the value of c minus c. which gives us, take 5 out of the side is negative, 3 is equal to negative c, or simply c is equal to 3. Our original expression, which is 6s plus 2 over s minus 1 s plus 2s plus 5 is equal to, a is 1, so it's 1 over s minus 1, b is minus 1, so we have plus, here this is negative, so we have minus s, c is 3, so this is minus s plus 3 over s squared plus 2s plus 5. Because this one is reducible, I want to rearrange it. So you can say s squared plus 2s plus 5. You can say this is equal to, see this middle term, it is 2, take half of it, so it is 2 divided by 2, 1. Say it is s plus 1 squared. I've already shown this in previous examples, but if we expand this one, if we expand it, we get s squared plus 2s plus 1. It means here what are you missing? So that they can be equal, we need to add a 4 plus 4. And therefore we can go ahead and say six s plus 2 over s minus 1 s plus 2s plus 5. I didn't want to use this color, I wanted to use green, but you can go ahead and use this one. See, this is 1 over s minus 1. Here you have a negative because it's positive and negative s plus 3 over s plus 1 squared plus 4. This one you can write it further as 1 over s minus 1 minus s plus 1 plus 2 over s plus 1 squared plus 4. See, the only thing I've done is I've split this 3 to 2 components, which is 1 and 2. We'll see why we need this one. This now becomes 1 over s minus 1 minus s plus 1 squared plus this 4, you can say it is 2 squared because they share the denominator. These 2 and these, they share the denominator. We can also say plus 2 over s plus 1 squared plus 2 squared. So that we can say the inverse Laplace transform of 6s plus 2 over s minus 1 s plus 2s plus 5 is the same as saying here we have to show it is inverse Laplace transform is the same as getting the inverse Laplace transform of 1 over s minus 1 minus s plus 1 s plus 1 squared plus 2 squared plus 2 over s plus 1 squared plus 2 squared. Then include that bracket. This being the fourth example on how to find the inverse Laplace transform, we even do not need to apply the inverse on each one of them separately. We know this inverse Laplace transform symbol apply to all of them, and therefore we can find the inverse Laplace transform of each one of them at a time and write the result here. See, this now finally becomes having done quite a number of examples. This one we should be able to see it will be exponential, negative, because here it is negative, here it will be positive, exponential t. Notice here you have s plus 1 and then you are squaring, and here you have s plus 1. This is a result of application of the first shift theorem. If you have not watched my videos on the shift theorem, watch the videos on the link shown here. This also again is a result of application of shift theorem. If you look at this one carefully here, there is an s here and there is a positive here. That one tells you it is, this positive first of all tells you it is trigonometric, and this s here tells you it is a cosine. So this is a result of getting the Laplace transform of a cos at multiplied by exponential at. This positive here again tells you this is a trigonometric function, and the constant here tells you this must be a sine function. So this is as a result of finding the Laplace transform of sine at multiplied by exponential negative at because of this positive sign here. So the inverse Laplace transform of this function here is, so you have a negative minus, because of this negative here, exponential, here we have positive s squared plus 1, s plus 1 squared, these are positive, so this must be a negative. Here our a is 1, therefore we are having negative 1t. We have said the whole function is cosine of our a here is 2, because this takes the form is of this form, s over s squared plus a squared, which is as a result of getting the Laplace transform of a cosine. Our a is 2, so it will be 2t plus, this is a result of a sine function. We have exponential negative t sine of 2t, exponential negative t sine of 2t. And that's how you should approach such kind of a question. The most important thing is to check the quadratic factor. By the way, here I had forgotten to put the square. I omitted the squares. The most important thing is to check first whether this factor is irreducible. Can you be able to factor it out further? If you can't, then you have to make some adjustment by rewriting that quadratic factor in this form. And in that way, you'll be able to apply the shift theorem. Now you can continue watching more videos online. By the way, if you do not know, online is the way to go, especially for us Kenyan youths, because there are so many opportunities online. Not only preparing for your next examination, but you could take some more online training. The biggest injustice you can do to yourself is to resist online learning, because in that way you'll be missing out on more opportunities that are there online.